In this video, I'll show how to do a numerical solution for a two-step reaction mechanism. And we'll see that it's just a little tiny bit different from doing a one-step mechanism. And once you've done this one, you can pretty much do any mechanism. So for the example, we'll look at a sequential reaction mechanism where A reacts to form B with rate constant K1, and B reacts to form two molecules of C with rate constant K2. And so with this mechanism, since those are simple mechanistic steps, we can see that the first step is, because it's unimolecular in A, it's going to be first order in A. And the second one, because it's unimolecular in B, will be first order in B. Okay, and the stoichiometry is 1 to 1 except for C, so we're making two molecules of C. And we'll have to keep that in mind when we write our rate equations in MATLAB. Let's take a look at the code and the output. All right, looking at this code. So first we have our block to clear the slate, and then let's get to work with our actual script. So down here we have, we start by putting in our constants. So in this case, I'm going to say that K1 and K2 are the same. And of course, if we want to see how that varies when we rerun the script, we can just change these numbers. Then we have our time span saying we're going to go from 0 to 40 seconds. And these are our initial concentrations. So when we have more than one species that we want to do a reaction profile for, we need to specify initial concentrations for each species. So as I say down here, we're going to have basically the first element in this vector is going to be the concentration of A, the second's concentration of B, and the third's concentration of C. So we're going to keep track of our concentrations in a single vector with each element being a different chemical. Okay, so you probably should put a key in for yourself, just reminding yourself that you're going to have this column vector X, and that you're going to store the elements. Each element in that vector is going to be a different concentration. Okay, so you might even want to comment your code to say that. Okay, so now we're going to set up the differential equation function. I'm just naming it sequential since it's a sequential mechanism. And you're going to say that x changes as a function of t. But keep in mind that x this time is a vector, so what you're really saying is that all three concentrations are going to change as a function of time. And then you specify, since we have x1 and x2 and x3, we're going to specify three different functions, one for each of the chemicals. So this is going to tell us the rate of change of A, this part is going to tell us the rate of change of B, and this is going to tell us the rate of change of C. So let's write in the expression for the individual rates of change of the products and reactants. So since A is a reactant and it's got a stoichiometry of 1, its rate of change is just the negative of that step, right? So every time the reaction takes a step forward, we use up one molecule of A. So there's a negative sign here, since this coefficient would be a -1, since it's a reactant. Okay, so we've got dA dt is negative K1 times A. B is a little more complicated because it's being made in this step, but then this step over here, it's being eaten up. So we have a positive change and a negative change, and that's reflected down here. In either case, a single molecule of B is being either made or destroyed, so we just have V1 minus V2. So we have our V1 and then a minus V2. Good. We have to be careful with C. C is being made in a single step, but every time this reaction takes a step forward, it uses up one B, but it makes two C. So we've got 2 has to be reflected in the fact that the rate of change of C is twice as fast as the rate of this step here. So dC dt is 2 times V2, or 2 times K2 times B. All right, so we have to do that analysis before we write the code. And I recommend writing out your mechanism, writing out the velocity of each step, and then writing expressions for your concentration derivatives. In other words, don't do this step and this step at the same time. Do them stepwise, otherwise it's really easy to forget one of these coefficients. All right, let's look at the code. Okay, So here are those rate equations. We said the rate of change of A is negative K1 times our concentration of A. The rate of change of B is the concentration of A times the first step. So this is our B production. And over here we've got minus K2 times B. So this is our rate of the second rate step eating up B. And then we have here the rate of the second step for producing C. So once again, it's K2 times B, concentration of B, but now we're multiplying times 2 since we're making 2 moles of C for every step the reaction takes forward. Great. So we've got each of our rate equations built in. And then once again, we tell it that we want to do the ordinary differential equation solver for this mechanism that we just called sequential over the time span. Remember, that's 0 to 40 seconds. And initial is going to be a vector where we have our initial conditions. So we don't have to have B and C start off at 0, but in this case we're going to have them be 0. So we're just starting off with A. We could change these if we wanted to start off with a non-zero amount of B and C. So whether you want to do that is just up to you for your particular application. Okay, so we threw in our time span, what our initial concentrations were, and then what we're going to do, it actually put all the answers into this. So this is T is a vector of times, and xcalc is going to be an array that has concentrations for A, B, and C separately as a function of time. So this is actually a matrix. And so what I'm doing in this plotting loop is going through and saying I want to pull out the concentrations one by one and put them all in one plot. You could do it a bunch of different ways. You don't have to use a loop. But what this does is it has a counter just called species, where species is species 1 would be A, species 2 would be B, and species 3 would be C. And as it steps through this loop, it goes through the loop 3 times, and each time it plots a different thing. So here it's plotting, for all of them it's going to be X, the x-axis is going to be T, and then xcalc, this is row column, so it's going to look into all the rows, but for the first time it goes through a loop, it's going to go and look at the first column, so it's going to be the A concentrations, and it's going to plot it, and it's going to go back through the loop and change this species to 2 the second time through the loop, and it's going to plot the second column, which is the concentration of B, and the third time through the loop it's going to plot the concentration of C. So you could actually have this as if it's less confusing for you, as 3 separate plot statements, but if you've got a lot of plots, then probably better to use a loop. And hold all just means that it's going to keep putting stuff on the same plot. It's not ever going to start over. Okay, and then I have some code down here just to make the plot look nice. So my concentrations are going to be in molarity, and my time is going to be in seconds. Okay, and if you put this last statement in here, it will make a file in your MATLAB folder. In this case, it'll be file name sequential reactions. It's going to be a PNG file at 300 dots per inch resolution. So that's something I could put into a document if I needed it later. Let's run this bit of code. Okay, so notice we had our A decreasing and our intermediate B built up and then reacted away. So notice the steady state assumption would not be good here. And that makes sense because it wasn't a slow followed by fast mechanism. Remember, we said these rate constants were about the same. If we pull them up here, we can see that they're actually identical. So we don't have a slow fast mechanism. Steady state assumption would have been wrong, and that's clearly shown in this graph here. And notice that our product C goes and asymptotes out at a concentration of 4, which makes sense because we started off with a molarity of A of 2, and the stoichiometry of the reaction was such that we should end up with twice as much C as we started with A. So there's our concentration profiles as a function of time.